Good morning, students. We are once again here to teach you electrochemistry. In the last lecture, as you have seen, we have studied the measurement of standard cell potential, and we found the equation of the standard cell potential as well as we studied the EMF series. In today's lecture, we are going to study the measurement of non-standard electrode potential, which can be derived if the conditions are temperature is not equals to 298 Kelvin, pressure is not equals to 1 atmosphere, and the concentration is not equals to 1 molar. In fact, it is not necessary that all the three conditions should be fulfilled. Even if one condition out of this is not there, then we can measure the non-standard electrode potential for a galvanic cell. Now, we know for a galvanic cell, in the galvanic cell, spontaneous redox reaction occurs, and we have studied what is a spontaneous redox reaction. That is, the reactions occur on its own. Now, in a galvanic cell, if you apply the principles of physics, the work is done by the galvanic cell, okay, because the volt is getting produced. So, work that is done by the cell can be written by the equation work done equals to Q into V, where Q is the charge flowing through the circuit. Okay, how does the charge flow? It is due to the movement of electrons. So, when you consider movement of electrons, the charge on 1 mole of electron was found to be 96500 coulombs. That is 96,500 coulombs, and it was equals to 1 Faraday. So, when we consider a galvanic cell wherein n number of electrons are flowing, the charge on n moles of electron will be equals to Nf. In the equation, V stands for the potential that is developed and which we observe on the voltmeter, and it is represented in the last lecture we have studied as E cell. So, substituting charge on n mole of electrons Nf in place of Q in the equation and the potential developed V as E cell, we get the equation of work done by the galvanic cell, which will be equals to NFE cell. Now, when you consider that a galvanic cell is functioning, as the cell goes on functioning, as the cell goes on operating, the useful energy is going on decreasing. And in terms of a galvanic cell, we know, we have studied in 11th standard that the useful energy of the cell is termed as Gibbs free energy, which is represented by the symbol G. And we can write that the work that is done by the cell is equals to minus, delta stands for change, minus change in Gibbs free energy, because as the cell goes on functioning, the Gibbs free energy is getting utilized and it is decreasing. Now, substituting these two equations, we get delta G is equals to minus NFE cell, which represents the relation between change in the Gibbs free energy with the cell potential. And similarly, this occurs, this is the equation in terms of non-standard condition. Once again, I am reminding, non-standard condition, temperature not equals to 298 Kelvin, pressure not equals to 1 atmosphere, concentration not equals to 1 molar. If the same cell functions in standard conditions, then the equation can be written as delta G naught, that is standard change in the free energy, is equals to minus NF E naught cell, where E naught cell stands for the standard cell potential, F is the current in Faraday, and N is the number of electrons. Now, how do you develop the standard cell potential? That we have calculated in the last lecture. On the basis of EMF series, we can calculate the standard cell potential of a cell. Okay, but in terms of non-standard cell potential, students, we need to remember a formula of thermodynamics chapter of standard 11th, which shows the relation between change in Gibbs free energy with the reaction quotient. And if you remember, this was the equation, delta G is equals to delta G naught plus RT ln Q. Change in Gibbs free energy is equals to standard change in Gibbs free energy plus R stands for gas constant, whose value is 8.314 joule mole inverse Kelvin inverse. Once again, it was a part of states of matter which you have studied. T is the temperature in Kelvin, and ln stands for natural log, Q stands for reaction quotient, which we again saw in equilibrium chapter. So, let us look at the substitution in this equation. Natural log can be written as log to the base e, which can be further written in the form of 2.303 log to the base 10. Now, substituting the equations of E cell and E naught cell for delta G and G naught, which we derived, we can write this equation as minus NFE cell is equals to minus NFE naught cell plus RT ln Q. Now, dividing this entire equation by the term NF minus NF, as you can see, we are dividing the entire equation by the term minus NF, we get the equation E cell is equals to E naught cell, because here NF will get cut, here also NF will get cut. So, we will get the equation E cell is equals to E naught cell minus RT upon NF ln Q. Now, in this equation, if the temperature is 298 Kelvin, R value is 8.314, F is 96500 coulombs, then substituting this we get the equation E cell equals to E naught cell minus 8.314 into 298 for temperature, ln Q we can write it as 2.303 log of Q. So, 2.303 log of Q. N stands for the number of electrons that are exchanged during the entire chemical reaction, and F, that is Faraday, 96500 coulombs. So, this entire value on calculation 8.314 into 298 into 2.303 divided by 96500, we get the value of 0.059. So, we get the equation E cell equals to E naught cell minus 0.059 upon N into log of Q. This equation is termed as Nernst equation to calculate the non-standard electrode potential of a cell. So, non-standard electrode potential of a cell can be known if we know the standard cell potential and the reaction quotient. Now, let us see how to calculate the reaction quotient of a given cell. Okay, so we have studied the derivation of Nernst equation as E cell equals to E naught cell minus 0.059 upon N log to the base 10 of reaction quotient. Now, let us study how to calculate the Nernst equation for a half cell and for a complete cell. Now, for a half cell, we can write the reduction reaction as, if the metal ion is represented as M raised to N plus, where N plus is the charge of the metal ion. When it accepts N number of electrons, it gets converted into 1 mole of metal. Then, in again equilibrium chapter of standard 11th, you have studied that the reaction quotient Q, the formula to calculate is equals to concentration of products divided by the concentration of reactants. Now, applying this formula in the equation for half cell, we can write reaction quotient Q for a half cell is equals to concentration of the products, that is the metal that is deposited on the electrode, which is in the solid form, divided by the concentration of the metal ion in the solution. We do not write the number of electrons as concentration. The square bracket here, student, represents the concentration. Now, for any solid substance, the active mass of metal solid will always be equals to 1. So, when we substitute here, we get the reaction quotient for a half cell is equals to 1 divided by concentration of the metal ion. Substituting this value in the equation of Nernst cell, we get E cell equals to E naught cell minus 0.059 upon n log of reaction quotient for a half cell, that is log of 1 divided by concentration of the metal ions in the solution. This is the equation. This is the Nernst equation to calculate the non-standard cell potential, the non-standard electrode potential of a half cell. Now, how do you calculate the standard electrode potential? We have already studied the standard electrode potential of a half cell given in the EMF series. So, for any given half cell we can substitute the values, we will look in the sum later on and we will get the value of E cell. Now, for a complete galvanic cell, let us assume this is the general equation for a complete galvanic cell, represented as, if you remember, minus sign indicates the anode part, plus sign indicates the cathode part, which we have studied in the second lecture. Cell representation: metal solid dipped in metal ion, X plus concentration C1, salt bridge which is connected with n number of metal ions having a concentration C2, in which there is the electrode dip which is of symbol N. So here if you look, for this given cell, the anode and the cathode reaction can be written as metal solid will give you m raised to x plus ions whose concentration is C1 and x moles of electrons are released in the solution. This shows the oxidation half reaction of the cell. For the cathode half reaction, reduction occurs wherein metal ion n raised to y plus whose concentration is C2 will accept, reduction occurs, y number of electrons and gets converted into 1 mole of metal and solid. Now, for any spontaneous redox reaction, the number of electrons that are exchanged should be equal. Okay, so multiplying the anodic half reaction by y and the cathodic half reaction by x to make the number of electrons equal, we get the equation y moles of m solid. Y moles of m solid will give you y moles of mx plus xy number of electrons. This will get x moles of n raised to y plus xy number of electrons gives you x into n. Cancelling the number of electrons exchanged because they will be equal xy number of electrons, we get the equation y moles of metal solid plus x moles of n raised to y plus whose concentration is Cu will give you y moles of metal x plus C1 plus x moles of n solid. Now, this is the net cell reaction that is occurring in the given galvanic cell. So, for this, if you calculate the reaction quotient from the formula concentration of products divided by concentration of reactants, this is the product side and this is the reactant side. So, we get this equation. And as I told you in previous, for half cell, metal solid, it is having active mass and for that the value will always be equals to 1. So, in the reaction quotient formula for a complete cell, substituting values of the unity 1 here, we get the reaction quotient of the complete cell as m raised to x plus concentration raised to y, n raised to y plus concentration raised to x. Now students, this is very confusing. In short, you can write that reaction quotient for a galvanic cell is equals to C1 concentration raised to y divided by C1 concentration raised to x. Now what is C1 concentration? If you look in the equation, C1 is the anode ion concentration and C2 is the cathode ion concentration. So for reaction quotient of the complete galvanic cell is equals to concentration of the anion divided by the concentration at the cationic part. That is basically, you can see, concentration at anode divided by concentration of the metal ion at the cathode. And in this equation, the number of electrons exchanged will be equals to xn, Y product. So in substituting this equation in the Nernst equation, we get E cell, that is cell potential equals to standard cell potential minus 0.059 upon N. In place of Q we will write log of anode ion concentration raised to Y divided by cathode ion concentration raised to X. So students, let us do a sum based on Nernst equation to calculate the cell potential. Take out your textbooks to textual exercise 3.5 and there are 4 sums. First sum we are doing it. Given is the cell representation where magnesium is the anode half cell and copper is the cathode half cell. So to calculate the net cell reaction and the number of electrons transferred, we can write the equation. Anode Mg solid gives you Mg2 plus 2 electrons. Cathode Cu2 plus will accept 2 electrons, gets converted into Cu solid. As you can see, the number of electrons exchanged are same. So both the electrons accepted and gained can be cancelled. So the net cell reaction we will get as Mg solid plus Cu2 plus 0.001 molar concentration gives you Mg2 plus 0.0001 molar plus Cu solid. Now this is a net cell equation on the basis of which we can write the Nernst equation. From this exchange of electrons we can say the total number of electrons exchanged, that is the value of N for this given half cell, is equals to 2. Now in the sum we can see that the standard reduction potential of magnesium is minus 2.36 volts and the standard reduction potential of copper is 0.34 volts. These values can be used to calculate the standard cell potential, that is E0 cell, which we have studied in the first lecture. E0 cell, if you remember the equation, is equals to standard reduction potential at cathode minus standard reduction potential at anode. Substituting the values 0.34 minus of minus 2.36, the value of standard cell potential comes equals to 2.70 volts. Now remember the Nernst equation. E cell equals to E0 cell minus 0.059 upon N log of C1 concentration raised to Y divided by C2 concentration raised to X. C1 again, if you remember, it is anode ion concentration. C2 is the cathode ion concentration. Substituting the values we get E0 cell 2.70 volts minus 0.059 upon N value we obtained as 2 log of concentration of the anode half cell 0.001 divided by concentration of the cathode half cell 0.0001. If you see, we will get the sum as 2.70 minus 0.0295 log of 10. Log of 10 is 1. So we get the answer of cell potential as 2.67 volts. Similarly, the remaining 3 sums you can do on your own, students. Thank you.